So today we're talking about acceleration, constant acceleration problems and constant velocity problems, but instead of in one dimension, we're going to be talking about them in two dimensions. And so we're going to be talking about things going down hills or up hills, and then we're also going to be talking about things moving in a circle. However, I'm going to start off the day with a little review of vector addition. And I want to explain it a little bit differently than I did last class, and I want you to think of it as like a tug of war. And so last class we kind of jumped right into vector addition in two dimensions, and I want to review what it is in one dimension. So we think of it as a tug of war, right? And you can also think of it as forces. And so if I've got a tug of war where I've got people pulling with, let's say 4 newtons of force to the left, and then I've got people pulling with 5 newtons of force to the right. Well, which way is that rope going to ultimately move? All right, so I know the stronger side is going to win, and it's going to be the side with people pulling 5 newtons worth of force. And the net result is actually going to be only 1 newton, and so it's the difference between those because they're acting in opposite directions. Likewise, I can have something pulling downward with a force of, 9.8, and we'll still say newtons for force. And then I could have somebody pulling upward on that same object also with 9.8 newtons. And what's going to happen in that case? Well, in that case, nothing is going to move. These two forces are going to cancel, and I'm not going to have any net force. And so I can begin to think of vectors as this kind of tug of war. When we move into two dimensions, this analogy actually still works. And so I can think, I like the example of someone in a rolly chair who is holding on 2 ropes. And so let's say we have our person in our chair, and one friend is going to pull the rope in this direction, and the other friend is going to pull the rope in this direction. And so these forces don't easily cancel or add or subtract or anything like that. And what I then think to myself is, okay, well, what is going to be the result of this pulling? So if I've got one person pulling up and then one person pulling right, what direction is the person in my rolly chair going to go? And I know that they're actually going to kind of go in this diagonal motion, right? And so that would be what we call the resultant of that action. Last class, you guys were asking, I could also think of this as a vector addition problem where I've got something going to the right and something going up, and I say, okay, are these tip to tail? No, they're not, so I actually need to move this arrow over, and now I can complete the triangle. And last class you guys were asking, well, how do I know if the arrow is going down and to the left or up and to the right? How do I know whether it's this arrow or that arrow? And the way that you decide is kind of thinking of this tug of war situation, right? If I've got something that is going to the right and up, then my net result is going to be a movement that is also to the right and up. Your book also has a really good example of this, and so if that example still isn't making sense to you, I really suggest you go to page 70 in your book, and these little tactics boxes are oftentimes pretty helpful. And so the way your book explains it, and this is a subtraction problem, so let's say I've got the problem of vector A, sorry about that. Let's say I have the problem of vector A minus vector B. So A minus B. In my mind, I'm going to go ahead and change that to an addition problem, so A plus the opposite of B. So I go ahead and draw vector A like they've done here. And then I have to flip vector B, and in my mind, all of that means is put the pointy end on the other end. So B is still the same size, but it's going the opposite way. And then to say, okay, well, once you've flipped B, place the tail of B at the tip of A, which is what we talked about. And then this last rule is kind of the question that somebody was getting at last class about, okay, well, where do I know or how do I know which arrow to draw? The one that's pointing up and to the right or down and to the left? And so your book says you've got to draw it from the tip of the first term to the tail of the second term. And so your arrow will always go from first term to second term, if you want to think about it like that. We also talked about acceleration vectors last class. Again, your book has a really great tactics box that explains this. But we can also think of it as vector addition. And so I know that acceleration is change in velocity over change in time. And I know that time is a scalar, so I'm not going to worry about that. And I'm going to bring down this delta V down here. It's V final minus V initial. Go ahead and change it to an addition problem. V final plus the opposite of V initial. And so I know I've got to flip my V initial vector. And then once I do that, my acceleration vector is actually going to be the resultant of those two, of that vector addition. And so we're going to continue on with this idea today. When we talk about things moving on a hill, we're going to talk about resultants, and we're going to talk about triangles, and we're going to talk about centripetal acceleration and exactly what that is. Alright, so again, a little bit of a review. We've talked about how to get the resultant of two vectors, and I've been really nice to you up to this point and given you those two vectors at a right angle to one another, and then the resultant is the hypotenuse. But you'll get to problems where they give you the hypotenuse and then they want you to find what we're calling the components of that vector. And so what is the x vector and what is the y vector? And that's what I've been giving you up to this point. If that vector is on a coordinate plane, I can very simply look and kind of follow it over and say, okay, the x vector is this many to the right, and the y vector is that many up. But on this particular one, I haven't given that to you. And so what I'm going to tell you for this particular one is that theta equals 30 degrees. And I'm going to tell you that vector A, which they've given you, is equal to 8. Right? And so then what I'm looking at is a simplified trig problem. And I've got to decide, okay, which trig function do I have to use? And so I know that sine of theta is equal to opposite over hypotenuse. I know that cosine of theta is equal to adjacent over hypotenuse. And I know that tangent of theta is equal to opposite over adjacent. And so I've got to choose, okay, what do I have here? I've got a theta, and I've got a, I've got a theta, and I've got a hypotenuse, and let's say that I'm going to ask you first for, well, what is the y component of this? In this particular triangle, the y is the opposite side, and so that leads me to the sine function. And so I plug in my values and I say, okay, I know that, I'm going to erase that cosine there, I know that I'm going to have sine of 30 degrees is equal to x, I don't really know what that opposite side is, that's what I'm trying to figure out, over the hypotenuse of 8. To solve for x, I need to multiply both sides by 8. On the right hand side, they cancel, and so in your calculator you'll need to put 8 times the sine of 30 degrees, and you'll need to make sure that you're in degree mode. Remember, we found that out the hard time last time we did trig functions. And so if you have one of those big graphing calculators that is under mode, and you'll go down to the third row and see if radian is highlighted. If it is, you need to switch over to degrees and hit enter before you can solve this problem. Once you do, you'll find that the y component is like 4 something, right? And so we can also use, we can deconstruct vectors to figure out what their components are, or simply their x's and their y's. The other thing on this side that I really want to alert you to is this word magnitude. You're going to see magnitude a lot in your problem solvings, and you're going to want to let it trip you up because you're going to skip over it. Magnitude is just a verbal form for the meaning of absolute value. And so we reviewed in class and I said, okay, well, what is the absolute value of -3? Well, it is 3. And so when we talk about the magnitude of a vector, it doesn't matter what the symbol is on it or the size, or I'm sorry, or the direction that it's pointing. What we're referring to is kind of the absolute value of that vector. And so you could pretend at some point that, let's say I give you 2 vectors and one is a 3 to the right and the other is a -10 to the left, and I say which one has a greater magnitude. Well, I'm asking which one has a greater absolute value, and it is in fact this one pointing to the left. Alright, and so this idea of deconstructing vectors also leads us to an interesting point. I know the tip to tail rule, I can do that every time, and I can use trig to figure things out, but you might get some points in time where you have some really messy problems, like both of the vectors that you're supposed to be adding are in the diagonal, right? And let's say they're like this, and I will call these vector A and vector B, and I'm going to pretend that each one of these squares is a 1 unit, and so this would be 1, 2, 3, and 4 all the way over here. And I'm just going to apply that to the whole graph. Alright, so I could do the tip to tail rule for these, right? Like I could move B all the way up to the end of A and do some trig, and I'd get this really funny thing. Or I can add the components of the vectors. And so when I look at A, right, I'll have the x component and the y component of each. A has an x component of 1, 2 to the right, and so I'm going to say, okay, I've got 2 to the right, and it has a y component of 1, 2, 3 in the upward direction, and so I've got 3. And then I've got vector B over here that has an x component of 2 to the left, right, and it actually only has a y component of 1 up. And so I can look at adding these components to one another. To the left and to the right cancel each other out to be no component in the x direction. And 3 up plus 1 up gives me 4 up. And so my resultant vector is actually 4 straight up. Right, and so I'm going to give you one more example on this particular problem. And I'm going to say, okay, let's see. I've got a vector going down this way, and I've got one going up and over this direction, and I'll call, again, let's see, we'll call that one A and this one B. When I come over here to add the components of each vector, I can say vector A, vector B, and I will put their x components here, their y components here, and go on to add them in that manner. Okay, so for A, it's got an x component of 1, 2, so I'm going to say it's got a 2 to the right, and it's got a y component of 2 in the upward direction, or in the y direction. For vector B, it also has an x component of 2 to the right, but it has a y component of -3 and in the downward direction, which is what that negative indicates. And so then I start to think of this as a tug of war, and I've got 2 to the right and then another 2 to the right, which would yield a total of 4 to the right. And if I've got in the y direction 2 pulling up and 3 pulling down, then my result is going to be 1 in the downward direction. And so my resultant is going to have an x component of 4 to the right and a component of 1 down. And so I'll come on over here, and that'll be my resultant, having 4 to the right and 1 down. All right, we're going to begin talking about motion on a ramp, and I'm going to do that in a second video.